There you go.
And managed to mute myself, and it took me longer to unmute any
Okay.
so I apologize. My name is Margaret Bucher. I'm coordinating the Southern Blue Ridge Fire Learning Network together with Beth Buchanan. And today we're fortunate to have Josh Kelly with the Western Carolina Alliance present his work on using LiDAR to look at forest conditions in western North Carolina. Wanted to acknowledge that Josh has been with our network for the past 6 years. He has been a key contributor to tools we've used to prioritize burns, and he pulled together a successful CFLR proposal that has provided funding for the Grandfather District to do a lot of really good restoration work. So we're really excited to have Josh develop another tool using LiDAR that's available for North Carolina. Look at where we really are with forest conditions in our network. So with that, I turn it over to Josh, and thank you.
Well, thank you, Margaret, and thanks everyone for joining this webinar. I invited several of you specifically because I wanted your ideas on how to optimize this process to make it as meaningful as possible for the work we all do. As most of you know, I work for the Western North Carolina Alliance, which is a grassroots environmental organization that's been around for 31 years now. Prior to WNCA, I was with a fantastic organization known as Wildlaw, and I'm glad to be working with another fantastic organization now. So this presentation is a draft. This is not a finished product. This is a sort of an example of a concept that I'm working on how to get at current conditions in the forest of Western North Carolina, particularly for the Nantahala-Pisgah Forest Plan revision. And in this presentation, I'm going to review LiDAR data products available for vegetation analysis, ecological zone models that many of us in the Southern Blue Ridge Fire Learning Network are familiar with, but folks outside the network won't be familiar with. Reviewing of GAP data briefly and LANDFIRE data products also somewhat briefly. And an analysis of example ecosystem, that would be pine oak heath, listed there as POE at the bottom of the slide. And also, I really hope for some good feedback and discussion at the end of the presentation. So thanks for being here. Several of you have seen a similar presentation that I have given with many of the same slides. I wasn't sure who all was going to join this, so I've included some slides that are going to be repeats for some of you. But please bear with me in this first part of the presentation. For those of you who haven't seen LiDAR data, these are some images I stole from various places, notably the Fusion software manuals. And Fusion is the software package that I've used to process the LiDAR data that I'll be showing you all. So LiDAR is a laser technology that in this case is deployed from an aircraft and emits particles and waves of light to the ground in the speed and intensity at which they bounce back to find three-dimensional points in space. On the right-hand side of the frame, you can see a redwood tree in profile. That's what it looks like with all the laser returns. That's from the website Landmark Trees. LiDAR data is in some parts of the country publicly available. There's also lots of private data sets out there that you will have to pay for. The LiDAR data viewer at the CLIC website is where I obtained the data for this project. And this is just a map showing where the data is present in all those red cross-hatched areas. Notice North Carolina has 3 different cross-hatchings. In the southeast was phase 1 of the LiDAR data acquisition in 2001. And the central part of the state was phase 2 in 2003, and then the far western part of the state was phase 3 in 2005. And the data gets progressively better with each, each phase that went by. So phase 3 is nearly 4 times as data rich as phase 2, which is more data rich than phase 1, which allows different things in different areas. I've used LiDAR extensively with some of my friends at the Eastern Native Tree Society, or now the Native Tree Society, a group that's devoted to the study of trees and are particularly interested in large trees. And we've used this quite a lot to locate some of the tallest trees in eastern North America. And these next LiDAR maps will all be from above. And generally these LiDAR maps are from above. I don't tend to tilt them to view in profile. This is a view of an exceptional tulip tree grove in Smoky Mountains National Park. There are numerous 180-foot tall tulip poplars in this stand, which is quite exceptional, as well as the height record northern red oak. And this is a second growth stand. It's about 100 years old. And you can see things as small as fallen trees, like that fallen locust in the foreground shows up in the canopy model. The tree on the right there is the tallest known tree in the eastern U.S. It's 192 feet tall and 6 foot in diameter at ground level. It's 118 feet off the ground before it sprouts its first branch. Really impressive tree. And on the left is what it looks like in LiDAR. This past year, the Southern Blue Ridge Fire Learning Network funded me to work on the creation of LiDAR models for canopy height, canopy closure, and shrub density for 129 quadrangles covering the purchase boundary of Nantahala-Pisgah National Forest. That ended up being more like 140 quads when it was all said and done. Canopy height models were produced at 9 and 20-foot cell sizes for Phase 3, and that includes 5 of the ranger districts in Nantahala-Pisgah National Forest. For the grandfather ranger district, unfortunately, that was part of the Phase 2 acquisition, and it only allows about a 40-foot cell size. Some people even prefer a 60-foot cell size. And as a note, there's a wonderful fellow named Doug Newcomb at the Fish and Wildlife Service office in Raleigh that has a publicly available 60-foot cell size model, canopy height model for the entire state, which would also be a possible tool for this project. So for the canopy height, I think some of the good applications are stand mapping, forest structure, characterization, possibly estimating carbon stocks and other things as well. This is a map, not the greatest contrast, but it shows the quadrangles and then in a black and white scale canopy height models. That's for everything but the Phase 2 area. And just to give you some examples of things that show up in canopy height as well as areas of tall trees, this is the Buck Creek Serpentine Barrens, that very open area in the oval. And on the left-hand side, you can see low canopy signature going up to the top of Corundum Knob. So this was in 2005, and I think since this time that there's been some more restoration work at the Serpentine Barrens to reintroduce fire over to that Corundum Knob area. And it'd be interesting to have a more current LiDAR image to see if it's also more open now. So here's what it looks like. This is Asheville, the arrow pointing toward the Forest Supervisor's office. So I've compared LiDAR oftentimes to sort of an aerial photo with numerical values for each pixel that denote height or cover or whatever physical attribute you're looking at with LiDAR. So there's the whole shebang with all the districts. That's what it looks like. That's about 3.8 million acres. And here's a 20-foot pixel size. That's Looking Glass Rock. You can see it's a granitic dome with a forested top, and you can see how much shorter the canopy is on top. And you can also see on the bottom left of the screen is John Rock, another granitic dome, and then a number of harvest units on the south part of the bottom part of the screen, and the Davidson River going through the middle of the fish hatchery over on the left side, for any of you familiar with that spot. You know, one thing to be aware of is that, like I said, the Phase 3 data is nearly 4 times as data rich as the Phase 2. So it allows for smaller pixel size. This is the difference between 20-foot pixel size on the left-hand side of the boundary and 40-foot pixel size on the right. And the 20-foot pixel size still has a smoother texture than the 40-foot pixel size. 40-foot pixel size still seems quite useful. You can see the variation in tree height with the landscape. You can see low canopies on ridges, high canopies in coves, former harvest units, roads and streams, et cetera. But it really just isn't as beautiful as the Phase 3 data, which is, by the way, not as beautiful as the data they have in places like, I'm not sure if any of you caught the presentation from the Dickey project in California, but they have beautiful LiDAR data, and they're doing very sophisticated things with it. The things I'm doing really aren't that sophisticated. So canopy cover is similar to the height models, but gives the numerical values from 0 to 100%. It's in 40-foot pixel size for phase 3 and 60-foot pixel size for phase 2. Rule of thumb for pixel size on canopy cover is that you want it to be about the size of the crown area of a canopy tree. And I think I got it about right at 40 foot for phase 3. And it's okay if it's larger, but you don't want it to be smaller than the crown of a tree, because you'll end up with probably inflated cover values. Unfortunately, ran into problems with the way returns were categorized in the phase 2 data and the way they interacted with Fusion software. I'll get to that later. We'll discuss that. That's one of the problems I'd like some help solving. And I think that the phase 2 models mated calibration with phase 3. So here's a schematic of canopy cover. It just looks at the first returns and the percentage of first returns that hit vegetation before they hit the ground. And in this case, looked at all vegetation above 15 feet in height for the canopy cover. So in this diagram, 76% of the returns hit vegetation before hitting the ground. Therefore, you have a 76% canopy closure. And here's canopy cover. You look at, so white is high cover, black is low cover. You see mostly a closed canopy forest across western North Carolina. This is one of my favorite low elevation pine oak forests. It's near Hot Springs. Nice shortleaf pine and post oak stand over in the upper right hand corner. You can see some ancient gnarly post oaks. Nice understory of Piptacedion and little bluestem. And right on the Tennessee line. And
are we allowed to ask questions?
You can, Gordon.
You just want to plow through this and ask questions later.
I'm open to a question or two during the presentation.
I'll try to keep it brief. Back to the canopy cover there, you said that the first return, so that these things are going, that one. So they're, the radar stuff's going down and it's hitting that, and then you said that you compare that to the ones that hit the bare ground. What if it hits, okay, look, see on the right-hand side there?
Mm-hmm.
Where you got that little shrub.
Mm-hmm. We see how that shrub is below the 3-meter height break?
Would that count as part of the canopy closure or not?
No, it does not. In this case, I set the height break at 15 feet. So any return below 15 feet in height was counted as not part of the canopy.
So that 3-meter, okay. So you can adjust that.
Yeah. So I used approximately 5 meters, but the North Carolina data are in feet and not meters.
Right, okay. All right, thanks.
Good question. So you can see this is a very open canopied site. It had a wildfire in 2001, and I believe it's had a subsequent prescribed fire as well. And so the area in the photo is pointed out there right on the Tennessee line. You can also see regeneration areas from the wildfire in canopy cover. Shrub density is the same routine as canopy cover, but it looks at all returns instead of just first returns, and focuses, in this case, on vegetation between 1 and 15 feet. Let me back up. I found it to be really excellent at identifying areas of dense evergreen shrubs, and I've been very impressed with this data set, actually. I said fairly impressive. I've actually been very impressed with it. So here's was an iteration of the map of shrub density. It's more complete at the current time, but I didn't take the time to make a new map. And again, high values are in white and low values are darker. And interesting patterns of shrub density across the region. One big pattern is that private lands seem to have lower shrub density than public lands, but needs a little bit more investigation. Could be that a lot of the high quality soils ended up on private land rather than public land, or it could be differences in disturbance regime. We don't really know. So this is the crappy data. This is the phase 2 data at 60-foot pixel size, and even in this data, you can see fire lines from Linville Gorge fire. So this is the Linville Gorge area. On the left, there's the Brushy Ridge fire that I believe was in 2000, and on the side of the line that didn't burn, there's a higher shrub density than on the side of the line that did burn. And same thing with the 98 Short-Off fire. Again, these data were from 2003, so the most recent fires from Linville Gorge aren't captured here. You can see there is a super, or was and still is generally super dense shrub density on Linville Mountain and Dodson Knob, and that may end up being a problem at some point. Just to give folks a look at a smaller scale view of this, this is a portion of the Tuckasegee Quad in Jackson County, North Carolina. This is phase 3 data, and all maps are this frame. Just want to show how this breaks down in the landscape. So try to fix your eye on the landscape and you know, take note of where the creeks are and the hollows and where the ridges are. And this is what canopy height looks like. And canopy height, of course, tall canopy areas tend to correspond to sheltered spots that are moister and have concave landforms and focused moisture. And north-facing slopes and east-facing slopes tend to be beneficial for height as well at mid-elevations. Same quad. Here's canopy cover, similar trends, and I've got it here broken into just broad classes, which I think the best way to use these canopy cover values and most of these values is in broad classes. It may be off a little bit to one side or the other of those breaks, but it should be off consistently both ways. So I'm hoping that the errors even out. It seems like a smooth data set in all the looking at it I've done. And again, you know, the higher canopy covers are generally on more sheltered sites, higher canopy forest, and lower canopied forests tend to be a little bit more open in their canopy cover. Pardon me, back up. So here's the same quad. I'm going to put a color IR photo from 1998 on top of this, and red colors on this are evergreen vegetation, mostly in this frame, mountain laurel and rhododendron. Mountain laurel would be the lighter red, and rhododendron would be the darker red. Pick one of those dark red spots as I change the slide, and you'll see how closely they correspond to the areas of high shrub density that LiDAR finds. I think it does a really, really good job with this. So just some discussion of strengths and limitations of LiDAR. Strengths, generally high resolution, especially for phase 3. Great for forest structure analysis, I think. Allows analysis across ownership, whereas we have, you know, at least some data on public land and the types of forests that are there and the age classes, et cetera. We really have nothing of the sort for private lands, and there's a need for that. And in a lot of cases, some of the state lands don't have that detailed information either. Also can capture natural disturbances. So we're not living in a vacuum where only human actions are what are affecting the vegetation. Some of the limitations are that this particular data set does not include species composition. More contemporary LiDAR actually can distinguish different species with the intensity values from the return. This was pretty early LiDAR acquisition and doesn't have that capability. And again, collected in 2003 and 2005, so there is, you know, a dated aspect to the data. It's only one point in time, and it's not as close to the present as we would like it to be, but I still think it's probably the best thing we have in this area, and I think we're really lucky to have it. LiDAR data can be used to help with plot data or to train to plot data, but the plots must be bigger than a hectare or larger. And there are some concerns about projection of the original data. The publicly available data from the CLIC website was apparently reprojected into state plane from a different projection, and there are some concerns that there could have been some shifting. I don't think it would have been more than on the order of a foot or two, but that could be enough to alter some studies. So if you're going to try to use this data for training to plots, be aware of those issues.
Josh, is that 1 hectare or 1/10 of a hectare?
1/10 of a hectare was supposed to be, 0.1 hectare, yeah, or a quarter acre. So one issue when using LiDAR to identify structure in forest is you have to be able to delineate openings in a forest versus non-forested areas. And because LiDAR will show these areas as having no canopy cover or low vegetation height or whatever the case. So one thing I looked into was the best way to distinguish forest from non-forest or natural vegetation from converted vegetation. I looked at the GAP data and LANDFIRE vegetation cover. And GAP data is, both these are nationally available, I believe. Both of them are pretty impressive data sets. The GAP data has over 500 classes. also includes a very coarse map of ecosystems and denotes, unfortunately, many small areas of forest as disturbed, and I apologize for some of the editing errors here. I was putting this together at the last minute as usual. But so it has this whole class of recently disturbed vegetation that corresponds to both people's lawns and to areas in the middle of the forest. And in comparison, LANDFIRE, it's a separate, the vegetation cover is separate from their ecosystem mapping. It includes different vegetation cover types, but they're not ecosystem types. It also includes percent cover for each vegetation type, so shrub cover, herb cover, forest cover. LANDFIRE consistently confuses glade communities with lawns and pastures, but it's predictable and it's manageable. And in fact, I think a knowledgeable person could easily use the LANDFIRE vegetation cover to map some of the rare rock outcrop communities in western North Carolina. I preferred the LANDFIRE because it was much more consistent in the types of errors. A lot of the places where the gap data show recently disturbed areas, LANDFIRE simply shows as areas of lower canopy cover, which seems to be the reality when I look at those areas on aerial photos or when I examine places that I know well. So here's just a broad overview of the two, gap data on the left and LANDFIRE on the right. You know, gap data is really pretty map at this scale. They're both pretty. Zoomed in here, this is southern Nantahala Wilderness, and Coweta Laboratory is on the right there. So that purple color on the LANDFIRE on the right is that semi-dry herbaceous vegetation that gets confused. That's the lawn around the Coweta Laboratory. That gets confused with glades. So I excluded all those values from this analysis. On the left, on the gap data, you see brown values scattered hither and yon all throughout the forest, and those are classified the same way that true human disturbance is, except for a lot of those are not true human disturbance. A lot of those are in the wilderness, and they're really just data errors, classification errors. So I like the way that LANDFIRE handles things a little bit better, and ended up using it for forest, non-forest. As far as mapping different ecosystems, we have this fantastic tool that both National Forest in North Carolina and Southern Blue Ridge Fire Learning Network have invested in pretty heavily. These ecological zone models that were developed by Steve Simone, Tom Collins, Gary Kaufman, Henry McNabb, and Chris Ulray. Steve Simone has continued this work and has refined it further and has created a more accurate product than the original project. It's now on its third iteration for western North Carolina. And this is a map showing the various areas where those data are either being created or have been created. And there's, at this point, a continuous coverage between North Georgia and way up into the Virgin Valley of Virginia. So a lot of uniformity there with the way things are classified. Also tends to be a lot more specific than LANDFIRE or gap data in its identification of these communities. So the basic idea is that natural communities occur in predictable, reoccurring places on the landscape, and they're dictated by landform, elevation, geology, precipitation, et cetera. Here's the slide showing heath bald off in the distance on the spine of a ridge, and there's Steve Simone putting in data points for those heath balds. The result is, this big multicolored map of all these different ecosystems, over 20 of them, and that's a large area. I think that's nearly 8 million acres, maybe 7 million acres from northeast Georgia up to nearly the Virginia line and a lot of East Tennessee. And this is a close-up of the Mount Mitchell area, the white being the spruce fir forest on top of Mount Mitchell, and then all those other colors being various ecosystems that occur on these discrete landscape positions. So before we go any further with digging into those ecosystems, I wanted to go back to that problem with cover data in phase 2 of the LiDAR. Errors, best I can tell, errors in the way the returns were classified prevented Fusion software from computing cover without the all switch. So that if cover was computed with just first returns, an error message would occur, and there would be a null output. And that changed with the all switch. The difference, though, with the all switch is it uses all returns and not first returns, which changes the values. Combined with the fewer returns compared to phase 3, this resulted in average cover of 30% for the phase 2 data compared to 69% for the phase 3 data. And that's a tricky problem because some of those phase 2 values were actually good values. Some of the values that said 5% cover are real 5% cover values, and some of them that say, 77% are real, somewhere in the neighborhood of 70 or 80% cover. But there are a lot of values that are incorrect, and they're sort of random. When I compared the two data sets in their zone of overlap, which I'll get to in a little bit, found that they were about 53% similar between phase 3 and phase 2. So what to do about that? I don't really know. I've tried a few things, and I'd love some more ideas. Here you can see that zone of overlap. On the left-hand side, the lighter colors correspond to higher cover values. On the right-hand side, lower cover values. The lower cover values, I mean, even with those lower values, you can see there's a nice landscape pattern happening. And really like to find a way to use these. What I did was I looked at that zone of overlap between the phase 2 and phase 3. And I did a number of things. I did unsupervised classifications. I did focal maximums, and all sorts of things to try to bring the phase 2 data into line with the phase 3 data. What I ended up having best success with was manual calibration. I would love to find some sort of statistical regression method to transform the phase 2 values in a way that maintained the beneficial or correct values and altered the incorrect values. But I'm not, don't have the expertise to know how to do that. And if anyone on the call does, I'd love to hear about it. Another possibility would be field sampling during the growing season and calibrating to field samples. What I ended up doing, though, was reclassifying the data until it looked as much as possible like the other data. So here is the phase 2 and the phase 3 data all together. I reclassified it in such a way that the phase 2 looks a lot more like phase 3. You can see, though, in the phase 2, and this is a relic of the difference in sampling, there are striations in the data going from southwest to northeast, and that's the route that the planes flew. And so zones of overlap have more dense returns than zones without overlap, and that's just something present in the data. And there are some spots like that present in the phase 3 data as well. And some of those may need to be smoothed out. As a particular example, I'm going to look at pine oak heath forest, and I'm going to look at it in the phase 2 data acquisition area. So this is the area that I think could potentially have the most problems because of the issues with the cover values, and also because the data just isn't as, there's just not as much data collected there. So pine oak heath forest, if any of you aren't familiar with it, it's a xerophytic vegetation type, a lot of times referred to as table mountain pine, pitch pine forest. It's one of the more fire-influenced ecosystems in the southern Appalachians. It's also thought to be fairly altered because of fire suppression, probably one of the more altered ecosystems. That being said, it occurs in landscape positions that aren't very attractive for human activity, generally steep slopes and ridges. And of the 212,000 acres of pine oak heath forest in the Nantahala-Pisgah proclamation boundary, only about 21,000 acres have been converted to other uses, according to the LANDFIRE forest versus non-forest query. In the Cherokee National Forest Landscape Restoration Initiative, this ecosystem was found to be one of the 2 most out-of-whack ecosystems on the forest, and I would guess that that's probably true for the Nantahala-Pisgah as well. So it probably will be a forest plan revision issue to try to deal with some of these out-of-whack ecosystems. As far as revenue generation from this ecosystem, there's pretty much none in the form of timber harvest. It's generally inoperable, low canopied forest, twisty trees, just not worth the cost of operating on these steep slopes. It does have, though, a high proportion of disturbance-dependent species, such as table mountain pine and numerous grasses and wildflowers, et cetera. Here's a look at a pine oak heath forest in Virginia that had a recent wildfire. Looks great. You notice that the canopy trees are absolutely just fine. They couldn't have cared less. You can see that the shrubs in the understory are toasted, and the forest is opened up a little bit. this is another pine oak heath forest in the Blue Ridge that is typical of pine oak heath these days, that hasn't seen fire in a long time. Really closed in, really dense shrub layer, closed canopy. So this is zooming into the grandfather district, and all of the purple areas here are pine oak heath forest, mapped as potential pine oak heath forest by the Steve Simone EcoZone model. And this includes all ownerships. This is not just Forest Service. I'm looking at it, taking an all lands approach to this. As a straw man for comparing the current conditions to what may be the natural range of variation, I'm using the LANDFIRE biophysical setting model for southern Appalachian montane pine forest and woodland. I've found this to be one of the more, in my opinion, more accurate of the LANDFIRE models, and I think it's quite useful. Not so coincidentally, I think, we have a lot of information about the disturbance regime historically of pine oak heath because of dendrochronology studies in several areas around the region. The three locations that I'm most familiar with would be the western side of Smoky Mountains National Park, in George Washington National Forest in Virginia, and on Linville Mountain and Pisgah National Forest. In all those areas, fire scars on tree rings found a frequent fire return interval of between 3 and 7 years. That fire return interval under a natural range of variation is expected, according to the Vegetation Dynamics Development Tool, to produce this assortment of different seral and structural classes, an early successional class, a mid-open class, a late open class, and a late closed class. And if you look at this chart, there are cover and height values given for each class. And so what I have done is I have reclassified the height data to be, the height LiDAR data to be within those height classes. So from 0 to 5 meters, that's early successional forest. And 5 to 10 meters, that would be mid-successional, et cetera. Late successional would be over 10 meters. So these are very low site index forests. So 10 meters is about 33 feet. 5 meters is about 16 feet. Not very productive at all. But, you know, under natural range of variation, there's expected to be about 60% of this ecosystem in open condition, a little more actually, and about 12% in early successional condition at any one time, and only 5% with a closed canopy. So again, I reclassified canopy height to 0 to 16 feet, 16 to 33 feet, and then 33 to 189. So I took the entire canopy height coverage and reclassified it specifically for pine oak heath, and then reclassified cover to 0 to 20%, 21 to 70%, and 71 to 100% as suggested by the LANDFIRE biophysical setting model. And then I did that with phase 3. With phase 2, I just looked at it alongside the phase 3 data classified in that way and tried to make the values as similar as possible manually. And then I reclassified shrubs into equal intervals of high, medium, and low. So, you know, between 0 and 33, 33 to 66, and 67 to 100, et cetera. Here are the results for pine oak heath forest in the grandfather district. I tested canopy cover values versus canopy height values by comparing early seral habitat. And I trust the canopy height values pretty well. And because canopy cover only looks at vegetation above 15 feet in height, a lot of those open areas are these early successional areas. So the canopy cover is the one I'm skeptical of because there's the problem with the creation of the model, and I've manually calibrated it. But when I looked at early seral in my manual calibration versus the early seral in the canopy height, it was 8.4% in the canopy height and 7.7% for the canopy cover. So I felt pretty good about that. Both of those round to 8%. As of just the beginning. I don't think I'm finished there by any means, but I felt pretty good about the way it came out, and it made me hope and believe that the canopy cover is still a useful data set in the phase 2 area. So just a statistic, there are about 52,000 acres of potential pine oak heath forest in the grandfather district across all ownerships. Age class-wise, this is based on canopy height numbers, 8% early seral, 13% mid-seral, 79% late seral, compared to 12, 28, and 60% NRV. And that, you know, that's the mid's a bit down, the late's a bit up, and the early's a bit low, but not super bad. But really breaks down when you start looking at the open versus closed structural classes, with 20% in the current condition versus 79% closed, 20% open versus 79% closed, compared to a predicted 70% open versus 8% closed with NRV, and the remainder being early succession. And then you add on top of that 76% of the ecosystem has a medium or high shrub density. So, probably 3/4 of those open and early canopy covers are going to have high shrub density, which is further going to degrade the condition of that ecosystem. So again, to look at those categories and numbers from LANDFIRE. And we have a fair amount of pine oak heath forest that looks like this today. This is along the what I call the Witness Rock Road, some people call the Lime Kiln Road, on Woods Mountain in the Grandfather District. It's got a very nice canopy, and you can see it's not by any means closed, and it shows up as an open canopy with the canopy cover, but it's got very dense shrubs in the understory. And that's a problem, and not only is it a problem, it's a restoration opportunity. It's a problem because it's so prevalent across the landscape. It's not a problem in any one particular place, but the fact that 3/4 of this ecosystem is in this high shrub density or medium shrub density category seems like a restoration issue. So this is still not yet complete for even the Grandfather District, but we showed you one district, and it's taken about 3 days' work to get here. I still need to intersect ages and structural classes with shrub density to see how that breaks down. I want to see how much of that early and open, those rarer and underrepresented cereal classes are degraded by high shrub density. And I'd like to split national forest ownership from other ownerships to reveal any differences in trends across ownership. And then, of course, complete the analysis of pine oak heath for the phase 3 portion, which is going to be 4/5 or more of the area. Of the study area. More next steps, because this is just a draft concept, and I've got you all on here to tell me how to make this better. I want to come up with an agreeable fix for the phase 2 cover data, a fix that most people are going to accept as legitimate and useful. If that can't be done, there's also the opportunity to use LANDFIRE cover data, but I really like the LiDAR data a lot more. When I look at it closely, the LiDAR data is a lot better. It would be much better to use it if we could figure out a way to do so. I'd like to come up with a shared understanding of minimum early successional patch size and how to classify smaller patches, because a lot of those early successional patches that I identified in the pine oak heath we're talking down into as small as 1/100th of an acre. And that's not a meaningful patch size. So it'd be nice to come up with an agreement, come up with an agreement about what the minimum patch size is. And then when we have these aggregations of these smaller patch size, what do we do with those? So if we have a lot of these 10th acre or 100th acre open areas, does that make that area forest an open forest instead of a closed forest? And then finally, calculate departure from a natural range of variation. And either use LANDFIRE models as a baseline for that range of variation or something else, but it'd be excellent to calculate departure for each of anywhere from 9 to 12 ecosystems across the forest. So I've run through that presentation, and I'd love it if folks have questions and discussion. And if you, hello?
Yeah. Hey. This is Ed.
Hey, Ed.
Hey, how are you?
Doing well. How are you doing?
Great. Doing well. Thanks for your presentation. I just had one thing to clarify, not being part of the Fire Learning Network. NRV, the natural range variation, that is portion of that's like the predicted values that come back from the LANDFIRE modeling tool. Is that correct?
Well, actually, natural range of variation, I think, is a bigger concept than LANDFIRE. There's a body of ecological and scientific literature around natural range of variation. Okay. Natural range of variation is basically defined as the condition, species composition, et cetera, of an ecosystem without human interference, essentially, or other times defined as a pre-settlement.
In your comparison that you did of the figures from I guess, data from your LiDAR work and you compared it to the natural range of variation, that natural range of variation was from
indeed. I used LiDAR, LANDFIRE as my straw man, natural range of variation.
Like a reference.
Yeah, so I use these classes. And these are developed by entering the known or expected disturbance regimes, such as wind, fire, ice, etc., landslides, for bugs, insects, disease, for an ecosystem, and the probabilities of those disturbances happening in any one place, and then running a 1,000-year simulation, and that produces, the simulation produces these percentages.
Okay. Cool. Thanks for clarifying that for me.
Good question.
Josh, this is Gordon. To your question that you just sort of asked us to look at from the wildlife end there, the patch size thing, and that to me is, it's certainly one of the challenges of the LiDAR stuff. It's identifying all these things, but you hit two of the big keys on there, so that's good that we're looking at the same thing there. That's going to be a challenge in some respects because that is going to be dependent on what species you're talking about. And given different species that you're talking about, it's also going to matter, what forest types you're in. Mm-hmm. So in some cases, for a certain species in a certain forest type, it might be a certain size and aggregation, and then it's going to be different somewhere else. So, in terms of us using this stuff, and by the way, thanks for all this hard work. I don't think, folks, I sat with you one day there and then try to do some of this at my desk, and for you to go through all those quads was quite a bit of heavy lifting. We appreciate it. But I think for in terms of us using this stuff for the wildlife analyses and so forth, I'd like to see probably like you've done with canopy classes or height classes. I mean, we're probably going to need to be looking at some similar sort of measure of the distribution of the sizes of these mm-hmm. patches. And so, for some species, small patches scattered throughout is going to be positive, and for some species, that's not going to help them. So, mm-hmm. So it's going to be, probably coming up with a series, and Kendrick and I'll be glad to sit down with you and give you some of those values. I can't pull those right off the top of my head right now, although I certainly have an idea of ranges, but classify, smaller patches, less than a half acre, those sort of things, and then 5, 20, 10, 20, that sort of thing. And mm-hmm. then you also mentioned another key point, which is sort of the contagion thing, or aggregation, and, how are they? There are differences, if it's just a small patch out in the middle of nowhere, but versus having a bunch of those patches within a certain area. Again, for subsets of species that we're interested in, those will need to be, sort of categorized differently. So I think you're on the right track for that. I think we would just need to sit down, and I guess you're looking for the wildlife perspective on that particular question. Maybe mm-hmm. other issues for plants, but we'll be glad to help you work up values for those patch sizes for certain species.
That'd be fantastic. That'd be really fantastic, because once these are converted into polygon form, it's not a big deal to just exclude the smaller patch sizes. Just query for patch sizes greater than a certain size. The aggregation question is a little more difficult, but still attackable.
Yeah, and I'm working on some other modeling from looking at habitat quality for certain species, and so once I sort of get those models tweaked, we can work together to get that make sure that those fit, that they're in a usable form for the models, mm-hmm. And that'll again help us with the analyses that we're all trying to do. So, but that's the fact that you're able to go down to such small patch sizes is great. There's a lot of structural questions, below that when you look at the different patches, species composition in some cases will matter. In some cases, it won't. Being able to identify what types of shrubs, whether you're talking about, like you say, a rhododendron or laurel versus something that's got a more diverse mix of shrub species and forms and that sort of thing. So,
in my observation, the shrub density picks up almost exclusively the evergreen shrubs. It really doesn't pick up deciduous shrubs. So it seems very reliable for that.
Okay.
Yeah, that's going to be a limitation. That's what I'm saying. You said
so you'd like to be able to find what values correspond to the deciduous shrubs.
That sort of the mix in a particular location would be nice. But just getting patch size and like you say, with some of the landform characteristics, you can probably make some educated guesses on that sort of thing. But
yeah, we should get together and talk about that deciduous shrub problem a little bit. I think that's definitely an attainable thing to figure out.
But Kendrick and I would be glad to. It's more than discussing over the phone can probably handle at this stage. But we'd be glad to work with you on that because we're looking at the same things, and this is going to be a wonderful tool for us.
Right.
This is Jean Lorbert. I work for the Nature Conservancy in Virginia, and that deciduous shrub issue is one that particularly intrigues me because I think you can make some inferences about species composition. If we're looking at oak regeneration, especially if we can tease out the presence or absence of several layers of vegetation, so canopy, mid-story, understory, or shrub, like you were saying. And I think if I saw a signature, I don't know if this is possible, but if I saw a signature where I've got canopy at 100 feet, I've got some mid-story layer at 40 feet, and then I've got something else at say 5 feet. And barring the presence of rhododendron, then I could definitely say, all right, we've probably got a nice red maple beech mid-story, and maybe some oak, and then perhaps a low layer of oaks below that. So the deciduous shrub, being able to pick that up at multiple levels would be really interesting to me.
And that's definitely attainable also. For the mid-story question, it'd take a reprocessing of the data set, but the data is all organized and ready to do that. So a lot of the hard work is done on that.
And I'm very new to LiDAR, and I forget your graphic where you showed the lasers coming down from the sky and hitting various strata. Can you pick up, if there's a 40-foot dogwood that's under a 100-foot poplar, and beneath both of those is a 5-foot oak, can you pick up all those layers if they're under each other, or do they have to be kind of separated in space a little bit?
No, you can absolutely pick up all the layers, and you can see in this schematic, the redwood, you can see all the canopy layers of the redwood, even though some are underneath the others. The caveat to that is it depends on the density of the data collection. So I would be more comfortable with that with phase 3 than phase 2 for sure.
Gotcha.
And really, even our phase 3 data from 2005 is sort of primitive now compared to the contemporary LiDAR data that's has multiple postings per meter. I think the phase 3 data has postings at under 2 meters, but not under a meter. I mean, if you want to go look at, I'd recommend that presentation from the folks at the Dinky Collaborative in California. They had some really impressive looking LiDAR data.
Okay, thank you.
And that's what's out there now, and that's what's been acquired in 2011 for the Tennessee side of Smoky Mountains National Park, and 2009 in Northeast Georgia, and a lot of South Carolina, I think, has better data as well. The stuff I've seen off of the Francis Marion National Forest has been fantastic. It's been out of sight.
Josh, this is Hugh. On the question of the minimum early succession patch size, I would argue that that's more of a question of natural range of variation rather than choosing a particular minimum size, because I think under natural conditions you would have a real range of those sizes, and to me it would be problematic in picking a minimum size as kind of an optimal. Of course, LANDFIRE has the problem is the lack of kind of a spatially explicit model that would give a an approximation of that natural range of variation. But my understanding is that there is a spatially explicit component of LANDFIRE that's supposed to be coming out this year, so that might be a tool to kind of get a picture of the range of sizes of the early succession patches.
Sure, sure. I think that would be a great approach if there was some sort of 1,000-year model that would spit out how many patches would be bigger than 1/10 of an acre, and how many bigger than an acre, and how many bigger than 100 acres, and all that would be fascinating for sure. I do think, though, that that there are sort of minimum effective patch sizes for different species, and it's different for, say, tree regeneration versus some vertebrate wildlife species. Because there's so many overlapping values.
I think that goes back to Gordon's point that it kind of depends on the particular species, and so rather than picking a particular species, I guess I would advocate using a spatially explicit model to give an approximation of what it would be under a natural range of variations.
I think that would be fantastic.
That's going to be extraordinarily difficult, but I think, I don't have an objection to that. What I'm simply saying is that, in terms of assessing what's out there and what might be out there, say you find some model that tries to estimate that, as difficult as that will be, that sort of range of sizes and dispersion of sizes will have a certain impact on wildlife populations. I mean, that's
absolutely what we can do now. I mean, what we can do is take a look at within those areas that are natural vegetation. We can absolutely take a look at what the distribution of current patch sizes for early successional habitat, at least what they were in 2005. And we can say, well, this is what it was in 2005. What are the trends? And have an idea of where we stand in a way that we really haven't in the past, in a very comprehensive way. So.
Hey, Josh, this is Kendrick Wade.
Hey, Kendrick.
I had a quick comment about the early material stage. As everyone's aware, the structural changes early on in early successional change fast. From the first year, you can have a foot or less is the vegetation height, and the very next year it's up 5 feet. And the implications of that for wildlife in particular can be extreme. Just in 5 years, a species that occupied an early successional patch would then no longer occupy that patch because it's grown up. Have you thought about finer divisions as far as the early successional? You think that's possible?
I think it's definitely possible, even as far as vegetation height, or what metric are you thinking of as an early succession?
The height seems to work really well. I mean, if it's less than a foot, you can sort of assume it's mostly herbaceous, and then as you go up, it gets more woody. But it changes so fast too. As far as having the LiDAR data up, I'm not so sure we have updates to the data to really get at that. That's sort of the thing I struggle with thinking about. That's
one of the downsides.
Right.
It's a snapshot as of 2005, and we can
more recently, are they?
I think there was a plan to use ARA funds for a reacquisition in North Carolina, and I think they were scrapped, unfortunately.
Now, for early successional specifically, could you use height as a surrogate for age? If all we have is the snapshot, can we just say, okay, this stand was pretty uniformly 20 feet tall, and maybe we have some sort of reasonable assessment of site index And so we can say, probably it's, a 10-year-old, clear cut or something like that.
Sure,
that might be one way
to. We can absolutely do that as what's happening as of 2005. I think we can say that, and we can make some assumptions based on, what's the trends on public and private land about, harvest rates and about fire and stuff like that. It really is too bad we don't have more current data, though. It'd be nice to have a more contemporary picture.
Yeah, it sounds like we won't be able to get to that except on maybe a 10-year, possibly. Because we talk about age class distribution across the forest. Structurally speaking, 1 to 5 years or 0 to 5 years, early successional, a lot more structural change happens than like 5 years from 40 to 45-year-old stand.
Right. Yeah, because plant growth is most rapid during that first 5 or 10 years.
Yep. Right.
And it's different between ecosystems too. So I'm not sure if it's appropriate to use the same height break for all ecosystems or not.
Correct. Exactly.
Yep.
But yeah, I guess at some point, it's sort of like the divisions you make as far as the early successional range of age is going to be determined on how quickly or how often the data is updated. Be able to track that. But this is I think this is cutting edge stuff on really getting at a lot of structural issues that we haven't been able to get at before regarding all types of ecological factors.
Yeah, we keep focusing on the early successional thing, which obviously is an issue we want to look at, but all the other structural information that you get here is a gold mine for the wildlife stuff and the models that we've tried to use over the years. So I'm looking forward to doing some of that.
And this is definitely publicly available. You're
not going to charge me?
No, I'm not going to charge you. No, the FLN paid for it. I think that means you get some of it. So far, I've got a copy. Gary Kaufman has a copy, and Hugh Irwin has a copy, including raw data. And the raw data you need to bring an external drive to get. You can get the rasters on thumb drive if you want, just with the rasters for the quads. But yeah, I need to make a date with Ryan Jacobs for sure to get him all that stuff, and you guys too.
Yep. Hey, I've got to run. I guess I'll see you next week. I may go out with you for a day there, and so we can chat a little more about.
Okay, great. Yeah, come Tuesday. The weather looks excellent.
Yeah, a little better than today. Hey, Josh, thanks
a lot, Josh.
So much. Appreciate all your
work.
Take care, man.
Bye.
Great job, Josh.
Okay.
Thank you, everyone. Thanks, everyone.
Yeah, great presentation, Josh.